Well, sorry about that mess there with the laptop me fits here, or the Microsoft OneNote software. Anyways, all right. So just to kind of backtrack on this, we have this x squared. We're splitting it up from 0 to 2, and maybe you're doing it in n subintervals, however, in 4, whatever. But you start out with your delta x being 2 minus 0 over n. And that's going to be your width on this thing, the 2 over n. Okay, and then the height will be 2 over n times I minus 1 if you're going to do the left-hand subinterval. Okay, so here's the height, here's the delta x, the width of each of those, and you're going from I being 1 up to n. Okay, so that's what we're getting into in terms of this formula right here. So here's your delta x. There's your f of 2i minus 1. Again, that gives you the left-hand side for I being 1 up to whatever n. And remember, this is f of x being x squared. So you plug this in and you square it, right? So there's the input squared. And this becomes, I'm going to talk through this one and then we're going to write another one out here. Otherwise, you guys will be listening to this awful video for another 40 minutes. But once you plug this in, so I'm going to go back here. Okay, you expand this I minus 1. You got 2 squared, I minus 1 squared. You got the n squared on the bottom, right? And you start cleaning this thing up. You can take out 8 over n cubed. Remember, n is a number right here, right? You take that number out, and then you've got the I squared minus the 2i plus 1. And you can use the formula here. So here's one of those summation formulas, minus 2, and you can use the formula from that one. There's the formula for that one. And then here's a constant. There's your c. So it's c times this n, right? So 1 times n right there. And you clean that up, and that's what you end up with. You can do it for any amount of subintervals. So if you want to make 4 rectangles, you let n be 4 and so on, but that's that lower sum function. You could do the same similar thing for the upper sum. This time you're just going to go the right hand, 2i over n, f of 2i over n instead of I minus 1. Okay, and there's your delta x right there, 2 over n. Work that out. That's right here. Well, notice that the lower sum, I'm sorry, right here, is 8 thirds minus 4 over n plus 4 over 3n squared. Well, if you let these rectangles, if you run the limit, if you just run the limit as n goes to infinity so that you have no error on this, if n goes to infinity, right, you got 4 over infinity, that goes to 0. This goes to 0, and you're left with 8 thirds. Let me go to the upper sum. The upper sum is 8 thirds. So you let n go to infinity again, an infinite amount of those subintervals, so that you're eliminating any error on that. That goes to 0. That goes to 0. Guess what the area is from 0 to 2? It's 8 thirds. And that's what this screen is showing you. If you run the limit on the lower sum as n goes to infinity, it's going to be the exact same thing if you run the limit on the upper sum. So your squeeze theorem, choice falls from the squeeze theorem. The choice of x on the ith subinterval does not affect the limit. So in other words, it doesn't matter if we took the left hand or the right hand or even the midpoint, because we're letting the number of subintervals go to infinity, running the limit on that. So it makes no difference. So here's the actual area. The area formula is the limit as n goes to infinity of the height times the width, but we're going to run an infinite amount of those subintervals, where delta x, right, is what you want to start with, is b minus a over n. Okay, so for example, if you're going to find the area bounded by x cubed, the vertical lines from 0 to 1, as shown in this figure here, we're going to start out with number 1, what's the width? delta x b minus a over n. Well, we're going from 0 to 1, so 1 minus 0 over n. So 1 over n. Number 2, and let's do like a right-hand approximation. You know, if I split this up and I did a right-hand approximation, okay, then it would just be that 1 over n times I for a right approximation. Okay, you know, so for if I was 1, you're doing it into 4, and then be 1/4, right? 1 times 1 over 4, and so on. So you start, boom, at your first spot right there. Okay, and that's going to be the right-hand approximation. This one. So the right hand as the endpoints here is what I'm going to do. So the area, the limit, then goes to infinity of the summation of f of I over n times our delta x 1 over n, from I being 1 up to n. Okay. Well, this ends up being, I'm going to use my formula, my function. So remember, f of x is x cubed. So this becomes the limit, n goes to infinity, summation I being 1 n of I over n cubed times 1 over n. So this becomes 1 to n. I got I cubed over n cubed. So I cubed over, I got n cubed on the bottom. I've also got an n right there. So n to the 4th. Now remember, this is a number, right? This n to the 4th. So I can take that out front. So this becomes the limit n goes to infinity of 1 over n to the 4th times the summation of I being 1 up to n of this I cubed. Now this I have a formula for right here, right? I have a formula for that. So this becomes limit n goes to infinity 1 over n to the 4th times. Now I'm going to use my formula for the I cubed. So if you look back however many pages that was, that summation ends up being n squared n plus 1 squared all over 4. Okay. So now if I expand that, I'm going to have to come over here. I'm sorry, you guys. Limit that goes to infinity, and I've got n squared, I've got n plus 1 expanded, so n squared plus 2n plus 1. This is all over this 4n to the 4th right there. So I got n to the 4th plus 2n squared plus n squared all over 4n to the 4th. Limit n goes to infinity. Limit n goes to infinity. Well, this is a 4th. This is 1/2, 1 over 2n squared. This is n squared over 4n to the 4th, so 1 over 4n squared. Oh, I'm sorry, that's a 2n right there. So that's n to the 3rd over 2n. Ah, gosh, that's a 3. What am I doing? It's a 3. That means that's just a 1. Either way, when I run the limit right here, that's going to go to 0 because I'm going to have this huge number in the denominator. That's going to go to 0. Guess what our area is? Our area is. You're going to look at those. We'll see you next time.